It is May 17th, 2018, and I am responding to a post from Paul Gradenwitz yesterday at ResearchGate. Sadly, Paul Gradenwitz takes about an hour to download a 20-minute video in the lowest resolution. So I don't know exactly how to resolve that issue, but I could, I'm open to suggestions. Okay, this is what I said earlier. Would the observer at the edge of plane now understand? Yes, if you clearly describe what you mean by now. Um, I know you mean now equals 13.7 billion years. So this is like the line for 13.7 billion years from the point of view of the observer who assigns my velocity. Okay, this is my velocity over here at 0.99 c. Then you know what plane of simultaneity he would be talking about. He's talking about this plane of simultaneity right here. And Paul said, you are right. What I meant was his proper time value is much less than the proper time value of the observer at the center of the plane. Okay, so, and that's correct. So looking here, you can see that this is the proper time, or this is the proper this is a measurement of the proper time. This hyperbolic arc is the measurement of the proper time. I think for 0.99 c, the ratio, the gamma factor, cosh of arctange of 0.99 is about 7. So here, if this is 1, then this is 1/7. The proper time of this world line, the proper time measured by that world line is about 1/7. And the proper time of this world line is 1, and if I extended this up, then this would be around 7. So this event doesn't happen in Earth's point of view until Earth is about 7 times 13.7 billion years. We can switch over to Nautilus's point of view, and in Nautilus's point of view, Earth, the Earth frame is only reached 1/7 of the 13.7 billion years, and he won't reach 1 year until the Nautilus reaches 7 times 13.7 billion years. It is said that the Nautiluses are quite intelligent. He doesn't know if they would grasp a Milne universe, so I can move this back and forth. And so that's this is basically the essence of it. That the relativity of simultaneity and the relativity of position is prominent in these should be considered prominent in these two models. And so I don't think it is a matter of intelligence so much as a matter of just kind of being adaptable and taking these two unfamiliar ideas into account, the relativity of position and relativity of simultaneity. All right, this thing about his time is much slower than the time for the observer in the origin is incorrect. The time, once I do a Lorentz transform to any point of view, any clock traveling along these lines, going straight forward into time, will be the fastest clocks. Any clock that is moving relative to these will be slower clocks. Now those are one set of Euclidean points. This is one set of Euclidean points. If we look from this point of view of this guy going this way, then this would be another set of Euclidean points. They would essentially, these would be the Euclidean points from that guy's point of view, because a point is that which has no part, but actually, I mean, from the definition of Euclidean points from Euclid's The Elements, a point is that which has no part. But when we recognize that points actually do have a part, they have a velocity, then the points are Euclidean points are a set of world lines in Minkowski geometry that do have velocity. So there is no one unique observer whose coordinates are Euclidean coordinates. It's just that every observer will say that my Euclidean points have zero velocity. Okay, so you can connect all observers that agree that space is 13.7 billion years old and compare their view. So basically that's something like that. All of the let's specify connect all Hubble observers. Oh man, lag. All Hubble observers that agree that space is 13.7 billion years, and that's going to basically form a hyperbolic arc in the space-time. But as I explored in the example above, where I imagine an impenetrable wall at 14 billion light years radius around the place of the explosion, and not all observers ever would reach the experience of seeing their proper time shows 13.7 billion years. That's true. No, these guys are going to hit that wall pretty hard, and they're going to be very young when that happens. About light aberration, Paul had some more communication with George Dishman. Okay, so Paul is saying you have to distinguish between a velocity component of the source that he shares with all objects of the universe and a velocity component that is unique for that source. I don't think so. That's exactly where we disagree. I think Milne would disagree with this point too. Well, for one thing, there is no shared velocity component with all of the objects in the universe. Not when they're all coming off at different velocities. You also have to agree that the universe can have an apparent rotational speed with tangential velocities so that the rotational direction is an unlimited faster than c. No, no way. The apparent rotational speed, the universe has a apparent, no, it does not. Not in Milne's model, not in mine. In the frame of the observatory, the whole universe rotates around in one day. What? Wait. Oh, apparent. Okay, yes, absolutely. You're talking about watching the universe from the Earth's surface. Okay. Oh, you should have said that. I'm sorry. Yes, if you're watching the universe from the Earth's surface, then the universe has an apparent rotational speed with tangential velocities to the directional direction that are unlimited faster than c. Yes. In the frame of the observatory, the whole universe rotates around in one day. Yes. I'm sorry, I misunderstood. In that frame, Proxima Centauri moves many times faster than the speed of light. It would be about 10,550 c, but who cares? Correct. It is not the star moving through space, but the star moving with space. Yes. The one component of the velocity the star shares with all objects could be interpreted as movement of space. Yes. I'll say that, yeah. Movement of the star through space. The variation, change of the movement of space gives rise to the observed aberration. Yes, pretty much. The proper motion of the star through space has no effect on the aberration. Um, hmm. Um, I'm not sure what is meant by that. Okay, the proper motion. This part, I think I need to come back to the beginning of this because this I'm still kind of confused by. And this part, you have to distinguish between a velocity component of the source that he shares with all objects in the universe. There is no such velocity component that he shares, and a velocity component that is unique for that source. Um, if we were doing, yeah, well, no. So I agree with everything kind of in between these lines, although I thought I didn't at first, but I'm a little confused about making a distinction between the motion of the star and the motion of space. Like I said, that's exactly why I said I want the observer at rest in his observation frame, and then it's just the velocity of the source. But there's no distinction because it's his space. Once you take the observer at rest, you've made his world line vertical, and once you've made his world line vertical, there's no distinction between a velocity component of the source that he shares with all objects in the universe. He doesn't share. Look at those lines. He's not sharing a velocity with all objects in the universe. He's all the objects in the universe are going at different velocities in Milne's model. And then the proper motion of the star through space has no effect on the aberration. No, it will. It and that's going to be significant when it comes to the brightness of the star. I mean, a proper motion of the star with respect to other Hubble flow. I think this is where he's messing up. He's not making a distinction between Hubble flow particles and the Euclidean points of space. He says, you can now try to change your view to an observer who is not subjected to the variation in the speed of space, sun view, and then you have in that frame the proper motion of the star through the space and the changing motion of the observer on the Earth. From that viewpoint, all motion of the observer adds to the aberration, and all motion from the star has no influence. Jump on another viewpoint, and the story gets different again. All right, let's make this distinction then. The motion of the observer adds to the aberration. Okay, so which aberration are we talking about? there's two things. Let's talk about observer aberration and source aberration. So observer aberration is actually going to take is actually we're sitting right here. We see a star over here. We accelerate that way. Guess what that does to the location of that star? We'll be right here, and we'll see the star that way. That star will actually move forward. It will aberrate. That's what's happening. This event, which is in the past, Lorentz transforms towards the direction in front of us. On the other hand, the source aberration, what happens there? The source aberration, I can do it in the same diagram. The source aberration has light coming out of this object going in those directions. When it goes this way, it changes. The light will have we got 1, 2, 1, 2, 3, 1, 2, 3. I'll put 4 over here. 3, 4, 2, 3, 4. And then on this side, it's going to go like that, that, and that. So you'll have more light coming out of this side and less light coming out of this side. And that is going to affect the radiation that you actually see. The star might be a little bit dimmer. Actually, you end up having just about the same amount of light coming from you, unless you really accelerate a lot, in which case, like a star could end up being made very bright that you're coming toward, and very dim that you're moving away from, because all of its light is going that way. Only a little